Hello, this is Professor Todd Elliott. In this video, I would like to look at basic BJT biasing. The idea of biasing is to establish the operating cue point. Q stands for quiescent. And anyway, it's essentially the intersection of the collector current IC and the collector to emitter voltage VCE, and where those points cross, that's the cue point. There's a number of different ways to bias the BJT. Some of the ways are collector bias, or collector feedback bias, I think it's called. Yeah. Feedback bias. There's base bias. There's emitter bias. There's voltage divider bias. We'll look at that a little bit later. Okay, and there's probably a couple more which I've forgotten about. I used to cover most of those in class, but say we had some adjustments in the hours, classroom hours, which we have the full 3 hours back in class now. So I think going forward, I'm going to bring some of these back, but I'll have to look at that. But it's nice to have that option again. So thank you for the college for bring that hour back. Anyway, so the basic bias is a simple or an easy, goes by different words, biasing method. It's not the best way, but it's a very has a very unstable cue point, which we'll take a look at. But anyway, so let's take a look at some specs first. So this is the 3904 transistor. This is the one that you have in your kit. This is an MPN. Okay, there's the schematic symbol. There's the what it physically looks like. So this is the flat side, and when you look at it from left to right, from the flat side, that's the flat, it's a emitter-based collector. It's a matched pair with a 3906. We'll look at that a little bit later. Sometimes called a complementary pair, which means they're designed by the manufacturer to work symmetrically. They're meant to work together. So anyway, this is just a partial data sheet. The real one's probably 5 or 6 pages long, but just a couple of key parameters here, which I've highlighted. One is the collector to emitter voltage. Okay, this is the absolute maximum rating, which means this is the limit of what the device is rated for. Okay, so it's rated for a collector to emitter voltage that does not exceed 40 volts. Okay, so if you're designing the circuit, you must not go beyond that. I mean, all the parameters are important. I'm just looking for, right now, for our discussions, which is the most important ones. The other one is the collector current, IC, the continuous. Sometimes I'll give you the peak current, which is like just it can handle sort of an overload for so much period of time, as long as it's not repetitive. This is the standard collector current. It handles internally that or continually. That's what it means. In which case, it's rated at 200 milliamps. Most likely, in the data sheet, it would spec. You have to have a little clip-on fin heatsink to get that much current out of it continually. And anyway, so those are the two main parameters that we need, just for the moment. Okay. The beta DC, we know from an earlier discussion that the beta DC is the DC current gain. We know it's not constant. It varies with temperature, which also means by default it varies with the current, because the more current flows through the transistor, the warmer, the hotter it gets. The transistor doesn't know, right? It's affected by its own the ambient, the air temperature, and also the temperature generated, through its operation, right? Doesn't know the difference, right? So that's going to vary the beta, and it's a parameter which cannot be well controlled. So this is the DC current gain, which is sometimes called HFE. H stands for H parameters, but it means the same thing. Notice how they give you some standard test specs, which is standard for a data sheet. They tell you how it's, here's the ratings and here's the conditions, because they want to make sure that you're not using it, over, and come back and, and say, well, your device didn't meet your specs. Well, yeah, it does, because we gave you some test guideline parameters to make sure you keep within that. Anyway, you can see then that, they give you different values of collector current and the collector to emitter voltage. But if I just look at this one right here, it says that if the collector current is 10 milliamps and the collector to emitter voltage is 1 volt, the current gain is going to be in the range of the 100 to 300. Okay, and that's up in the active or linear operating range when you look at the collector curve. Okay. Okay. So this is the reverse bias. So this is the breakdown. If you reverse bias the collector to emitter junction, it has a maximum rating of 40 volts. Okay. The collector to emitter saturation voltage, again, it gives you the test parameters. It says it's in 0.2 to 0.3. Okay. So just as a rule of thumb, VCE saturation is generally 100 to 300 millivolts. Okay, so they can, once again, and we looked at this earlier, this is the collector curve. We have the collector to emitter voltage here, the collector current here, 40 volts. That was the maximum for the 3904. That was its maximum forward collector to emitter voltage. It's 40 volts. If you go beyond that, it's going to destroy the transistor. If the collector to emitter voltage is 0.7 volts, and that is not, again, it's going to vary a little bit on the transistor, so that's not a fine line. I like to call that a fuzzy line, so it's right around 0.7. Taking transistors out of the bag, some might be 0.68, others might be 0.72, but it's around 0.7. That's the threshold between saturation and the active linear range. And what it was saying then on the specification, if you're up in this range, then the typical current gain is going to be somewhere in the 100 to 300 range. And if you're down below 0.7, it's going to be saturated, and the current gain is going to be much less. Okay, so anyway, we'll look at the saturated region in the next presentation on the transistor switch. But if you want the high linear current gain, then you need to have VCE needs to be at least 0.7. And even at 0.7, it's still kind of, in the saturated. So typically you want it VCE probably at least a volt, just to give us a little bit of buffer there. But anyway. Okay. NPN base bias. Okay, so here we used one power supply, VCC, for the collector to emitter loop. And then we're going to use power supply VBB to supply the base to emitter loop. Normally you wouldn't use two power supplies, but with the, it's not always true, with the emitter bias, which provides a very stable Q point, is great for amplifiers. It does require a split plus minus power supply, but anyway, we could easily have done this using one power supply, but I find that for, initial educational, if you like, purposes, having the two power supplies just makes it a little bit easier for students to visualize. So that's the way I do it. Take note of the voltages. Okay, so we have the voltage across the collector resistor. That's VRC. The collector voltage is VC, is down to the common ground. Collector to emitter voltage is between those 2 points there. The emitter voltage is from the emitter to ground, which in this case, because the emitter is directly grounded, in this case the emitter voltage is 0. When we move on to the voltage divider, there will be a resistor there, so that will not be the case, but for this circuit it is. And the base voltage is from VB is from the base all the way down to the ground. Okay, so take note of that. Okay, so these are just some important notes here. I'm not going to reiterate them. You can pause the presentation and write those down. I would highly recommend it. Okay. All right. Sample problem number 1. Okay. Right. So we're going to solve for all the voltages and current. We're going to assume the current gain is 150. Again, we don't really know what the current gain is. We know we want it. We're going to bias it so it's in the active region. So we know the current gain is going to be, roughly in the 100 to 300 range. Okay, so those are the component values. So I'd encourage you to pause and write that down. I'm not going to refer back to this slide again. I'm just going to go ahead and solve it, and then you can make the notes later. But me flipping back and forth, I don't think it's going to be. I think it's going to be counterproductive, and it'll just be confusing for you. So I'm just going to go ahead and solve it, and I've already solved this in advance, but I'm going to write down all the steps for you. So take a copy, screenshot, print, write by hand, whatever. Have this in front of you, and then let's go ahead and solve it step by step. Okay. So step 1. Okay, the voltage across base resistor RB, call it VRB. It's going to be VBB minus the base to emitter voltage. So that's 5. So unless I tell you otherwise, assume VBE is 0.7. Practically, it might not. It's going to wiggle a little bit, but we'll assume it's the ideal 0.7. So that equals 4.3 volts. Step 2. The base current equals VRB. This is just Ohm's law. Okay. 86 microamps. Okay, for 3, the collector current, which we know is 99.9% equal to the emitter current, is equal to the base current multiplied by the current gain. So if you're up in the linear operating region, this is true. If you're saturated, the collector current is going to be not because it's not linear, will be not beta times larger. It's the beta is going to be much larger, so it's a non-linear relationship. But in the active region, it's a nice, perfectly linear relationship, which is what we want in this case. Anyway, that's going to be equal to the base current 86 times our assumed beta of 150 equals 12.9 milliamps. Okay, so I would recommend putting the microamps as the milliamps, however you want to do it, before you put it in a calculator. But anyway, that is the collector current. Okay. Okay, so the collector resistor voltage, VRC, again, I'm simply using Ohm's law, times equals 6.45 volts. The collector to emitter voltage, again, you need to have the drawing in front of you, and I'm just assuming you are as you're going through this, is equal to okay. So because that's significantly greater than our 0.7 volts, we know this is up in the linear area. And that's what we have. That's the only way we can have our high current gain. Okay, 6. The emitter voltage is equal to 0 volts because it's directly, look back at the drawing, tied to ground. Okay, so let's look at the DC low line. There is an AC low line, which we're not doing. Not that it's not important, but we only have so much time, I guess. So this is going to be the relationship. It's regardless of the circuit. Ugh, that's really not very straight, is it? It's always the relationship between two parameters, which I explained earlier, VCE and IC, and it's a line that looks like that. This is going to be IC sat, and this is going to be VCE off. Okay, by standard convention, this is the saturation current, which is like the maximum current if that transistor for the given resistor and values and the power supply voltages, if that transistor was able to turn on perfectly 100%, how much current would flow. So in this case, we assume VCE equals 0, and we know it can't ever quite reach that, but by convention, this is the way these are drawn. What is the saturation current? So we're going to calculate that. And then the other one is VCE off, and then we assume that the collector current is equal to 0. Okay, so I'm going to go one slide back. We're going to write all this out, then we'll come back and put the numbers on. Okay, I just don't have the room. Milliamps, sorry. Okay, so this would be 24. That's the upper end of the low line. Anyway, so this is going to be 12 volts. So that's the lower end of the low line. Now, you don't need to draw this. I like to because it gives me a frame of reference. If we were to fix the Q point exactly in the center there, Okay, so it's halfway between IC sat and VCE. That means then that this, if the Q point was at the midpoint, then this is going to be half VCE. So this is 6. And IC would be half IC sat, would be 12. Okay, this is just to help give us some scale. You by no means have to plot at this, but I find it helpful. The actual collector current was 12.9 milliamps. So we're very close to being in the center. I'm going to have to exaggerate this just so you can simply see it. Okay. Right, so this was our calculated current where our Q point really is, and VCE is going to be at, and again, I've had to pull that back more than it really is, just so you can see it. But anyway, that's the low line. I don't draw them for every circuit, but I draw them for a number of them. It helps you visualize what's going on in the circuit. So what I'm going to leave you, we have some more to do, but what I would like you to do for homework, and I am not taking this up, okay, is to repeat this whole problem from all the calculations to the low line. So recalculate, right? Assume the beta DC is 85, and then redo it again at 175. And you need the practice. Okay, it's good exercise. You'll find that the Q point, so compare the parameters for the original beta and for the beta at 175 and 85, compare what IC and compare what VCE is, and you'll find that the Q point is unstable. So if you're using this in a switching application, which we're going to do in the next presentation, then fine, no problem. Not good for an amplifier because you don't want an unstable Q point. In that application, you're going to use the voltage divider or the emitter bias. But anyway, okay, so work on that. Okay, so IC sat. Okay, if we visualize VCE is equal to 0, that is the same assumption for all BJT biasing. The formula will vary depending on the circuit. For this particular circuit, again, have it in front of you. IC sat is simply equal to VCC divided by RC. So that was 500 ohms is 24 miles. Okay, anyway. VCE off, and we assume that the transistor isn't cut off, and we assume that the collector current is equal to 0, right? But in reality, there's a little bit of leakage current due to the high resistance between the collector and the emitter, but by convention, we assume it's 0. Okay. So, therefore, then, if there's no current flowing through the collector, so if IC is equal to 0, the collector resistor voltage is equal to 0, and therefore VCE is equal to 12 volts. In reality, this will be like 11.99, so this is a very slight approximation, but we're going to go on then to problem number 2. It's exactly the same circuit, simply just changed all the parameters. So you can write that down, and we're going to go through the same exercise. Okay. Oops. So again, be absolutely clear that certain that you have the circuit in front of you. Okay. So instead of solving the resistor voltage VRB, I'm just going to go right to IB. So okay, so that's okay. So that's the base current. Okay. Number 2. The collector current, which is essentially the same as the emitter current, is equal to the base current times the beta .73. Okay, again, it's important that you have the circuit in front of you, and then you can write all these steps down and follow it through, and then make a cohesive set of notes. I just can't, on an iPad, I just don't have the screen space. I can't, I'm sorry, I just can't do it all on one screen. In class, it's not, in person, it's not a problem, but this is the best I can do, but it'll be okay. So collector resistor voltage, VCE, okay. So again, we're much greater than the 0.7. So we know we're up in the active linear region. Okay. Okay, again, I'm going to calculate the load line. I'm just going to go ahead and do it. I explained in the last one all the different bits. So VCE, and this is going to be IC. Okay, so again, turn it back. So I have the circuit in front of me. Okay. I just want this to clear that up. So at cutoff, so this point here is called VCC off, which is cut off, and it's essentially equal to VCC. I'm just running out of room here. 18 volts. The saturation current, IC, is VCC divided by RC equals 18 milliamps. If the Q point was precise at 50%, this would be at 9, and this would be at 9 volts, so half this and half IC sat. And compare that to actually the values that we have. Okay, so The actual current is 9.73. Again, I pre-designed these to put the Q point close to the 50%. Okay, so this is where the Q point in fact is. Okay, and I've had to exaggerate that. So that is 9.73. And then VCE 8.2, 7 volts right there. Okay. Again, homework. Okay. And it's repetitive. I know, but that's good. Repetition is always good. Okay, so recalculate. Do everything again. Equals 90, and then let's just go with 180. Okay. Now, for the first problem, if you really if you got it down, you don't have to do this. I mean, you're gonna do this on your own. I'm not taking this up, but I'm just giving you some further work to do to refine your skill set. So anyway, it's up to you. Okay, so let's move on to the PNP transistor. This is the 3906. It's a complementary complement of the 3904, so let's call it complementary pair. Okay, so there's the schematic symbol. There's the flat side. There's the pinout. There's the flat. Okay. All right, so because it's a complementary pair, we're expecting the specifications to be the same. Saturation voltage under various test conditions. Okay, and very similar to the 3904. Okay, so we have the same circuit. Notice the change in the transistor. So now it's a PNP. Okay, notice that VCC and VBB are both negative power supplies, and it has to be that way. With the emitter voltage tied to ground, and the emitter needs to be more positive than the base. So if the emitter is at 0, the only way to make that more positive than the base voltage is to make the base voltage a negative voltage, hence the negative VBB. Okay, so anyway, take note of all that. I'm going to flip over to my page, and then we are going to go ahead and solve this. Okay, make sure you have this drawing right in front of you. Okay, otherwise it's going to be it's not going to make any sense at all. Okay, so write the equation: VBB plus base resistor voltage. So that's just summing the voltages around the base to emitter loop. I don't always show it like this, but I'm doing this for a reason. Okay, therefore we can say then that VRB equals VBB plus 0.7 equals minus 8 plus 0.7 equals minus 7.3. Okay, correct way, like is shown here, that's fine. I could also say, and this is the way I normally do it. When I'm dealing with negative voltages, it just in my mind, this just makes more sense, right? I just ignore the negative voltage, right? So I know this is 8, and I know this is 0.7, and I know this is 7.3. Okay, but because the power source is negative, all the voltages are going to be negative, right? I just stick the negative in later. Okay, so that's the way I do it. If you want to do it the mathematically, I prefer it this way. It's just simple for me to understand, like, right? So if VBB is negative, obviously this voltage is going to be negative. Okay, just logically, right? So anyway, okay, so step 2, base current. Okay. Drop the negative, please. Right? All right. I guess technically you could say the current should be minus 73 microamps. What's that really mean? The current's really going the opposite way than you think it is, but it's still 73 microamps. So to me, trying to keep the negative sign on the currents is just, it's a pointless exercise, and it just makes things more confusing. For the voltages, it's a different story, but for the current, just drop the negative, and your life will be a lot easier. Okay, right? 3, the collector current, of course, is essentially equal to the emitter current. Up in the active region, it's IB times the beta. Again, please don't put a negative on this. If on the test you were to put a negative on there, I will simply ignore it. Okay, if it's a negative voltage and you don't put a negative on the test, you will lose points. Okay, so with the current, it's really pointless to show that. Right? So, and again, if this were AC, right, and you can use use the DC bias to establish the Q point, but then in an amplifier you couple in the AC signal. Okay, there's AC current. It's going both ways, so it's kind of pointless, irrelevant to put a plus or minus because it's going both ways anyway. So anyway, just leave it off. I like keeping things simple. Okay, collector emitter voltage. Now, go back to the drawing. VCC is negative. So we know that's going to be negative, so we're just going to stick that in with the 10.95. Okay, that's how I do it, and I never get confused on that. Okay, VCE is equal to VCC minus VRC. Okay, again, I'm just gonna, to avoid getting confused in the math, I know if my power source is 16 volts, okay, and I know the collector to emitter voltage is equal to 10.95, then by Kirchhoff's voltage law, the balance must be to the collector to emitter. Okay. And again, right, I stuck that negative in because VCC is negative, so VCE has to be negative as well. Okay, so anyway, I guess technically it would be minus 16 plus 10.95. Honestly, mathematically, honestly, I find it more confusing to think of it that way. So Kirchhoff's voltage law says the sum of the voltages around the loop must add up to the source. So throw away the negative and just stick it in at the end if you need it. So anyway, why make it hard, right? Okay, you could do the load line exactly the same way as we did it before if you wanted to. I don't do it for everyone. It helps you understand where we're at. The only difference is just record the voltages as negative, but it's exactly the same. Okay, problem number 2. Okay, take note of all that. Let's go ahead and then solve it. Okay. All right. So 1, and this time I'm going to calculate the base resistor voltage. Do you need to? If I ask you for it, you do. If I don't, then you just want the current, you can do it in one step like we did before, but whatever. Never makes sense to you, right? So the more you play around with the circuits, okay, the more comfortable you get with them. And like anything, you only become proficient by doing. So that's what I recommend. Again, VBB is negative, so VRB must naturally be negative. Okay, so we'll just add the negative in at the end. The base current, please record it just as an absolute value. Recording the base current as a negative to me is totally irrelevant. Again, you'll have to make your own notes and stitch this all together with the circuit side by side to make this coherent and understandable for you. I just can't do it all on one screen. Again, for one or both of these problems, then I would strongly recommend that you just pick two different betas and then recalculate it. And what you're going to see is that IC and VCE moves quite a lot. Therefore, the key point is unstable because this biasing arrangement does not do a very good job at stabilizing the Q point. So this is, if the Q point, if it needs to be fixed in a certain spot, this is not a good application, not a good biasing method for that application. But can be for a switching application, totally acceptable. Okay. So again, it always depends. VRC. All right. VCC is negative. VRC must also be negative, just like that. VCE equals VCC. Okay, just don't get lost in the negatives, please. And VCC is negative, so therefore VCE must also be negative. Okay, so again, for homework, practice, okay, which you can decide to do or not. I recommend you do it for practice, but it's whatever you're comfortable with, I guess. Let the beta, let it be, I don't know, let's go 120, and then maybe, what was it, 90, so let's make it 80, okay? And then just go and just see where the Q point. Okay, so this biasing method, it's a simple, basic, easy biasing, whatever term you want to use. It works. It's not good for an amplifier because the Q point is highly unstable. For an amplifier, you will use the emitter bias or the voltage divider. So I'll probably start teaching the emitter bias again, probably next winter, because I have the extra class time now. But anyway, we'll look at the voltage divider next. It works. It's almost as good as as stable as the emitter bias, but doesn't require a split DC power supply. So anyway, that's it. Thanks for bearing with me through the whole thing. Again, please, as you watch the video, make extensive notes. Just watching the video on its own is not, it's useful, but it's not going to get, you're not going to get as much out of it. You really need to write everything out for yourself and write it in a way that makes sense for you. That's the method I've always used, and it's always worked for me. So, but anyway, you know how you learn the best. So So whatever works for you, that's what I recommend that you do. So anyway, have a wonderful day. Many blessings. Bye bye.